is the bottleneck really tied to how you're storing the information and the very nuts and bolts, the mechanics of that? It's not these elegant mathematical techniques, it's just how you store it?
For the majority part, it's a combination of different variables when you're thinking about the latency of processing the single query. So usually you need to get the execution plan right, meaning that whenever a database is faced with a query, the database would build something that is known as an execution plan. Basically, it's a set of steps that the database would need to run in order to produce the right result. And there could be different execution plans which would give you the same result, but the overall runtime of each plan differs. You really want to produce the right execution plan for the given query. So if you're messing up this part, you can usually throw performance out of the window. But let's say that you've managed to build a performant execution plan for a given query. Now, with Graph, it's a lot about traversing. For example, each time that you traverse a single node, for example, with adjacency lists and linked lists, you're accessing memory randomly. So every time you're accessing a different memory allocation in terms of address spaces, or if you need to go fetch some data from disk, then you're gonna really hurt your performance. With FalkorDB or with this sparse matrix approach, all of the data is laid out continuously. So usually memory access is very performant. Next up, when we're able to do multi-source BFS, meaning that we can, in parallel, traverse a graph from multiple sources and spread out. And lastly, maybe, is that traversing via matrix multiplication can easily take advantage of multi-threading. And so that what GraphQL does is basically doing for us, it's basically doing multi-source BFS in parallel. And the memory access is fantastic.